Okay, as far as I can see, we have Isabel, Andy, and Judith aren't here right now. But there you are, Judith. Did not recognize you. Okay, so we're going to review for the exam and then do some problems. First, I'm sorry. I was excited to get out of here on Friday before break, and I forgot to post homework there. So I let you know via the messaging system in Moodle. I think I put up the homework assignment finally on Wednesday, like the day before Thanksgiving. And I want you to be able to enjoy your vacation, not like, oh, look, it's Thanksgiving Day. I better do some physics all day. And so I incremented the number of drop assignments. But I still put it in there due on Monday because doing it will help you on the test. But you have one more drop assignment, which means that if you didn't have time to do it, it won't hurt your grade from what you would have had if I hadn't assigned it. But if you do it and you do better than your previous lower 3, then it raises your grade. So compared to what the rules were for the class when we started the semester, that homework can't hurt your grade. It can only help your grade. Right? I figure that's a fair way of doing things.
And
yes.
It's still due tonight, correct?
Right. Because it's beneficial for the test tomorrow. Doing it after the test wouldn't help you. I mean, wouldn't help you on the, Randy.
When you say homework assignments, do Perusals have homework assignments when you have to? Or is that just?
That's a separate thing. And I did fix the Perusal assignment schedule for the rest of the year. It should be all good. And you know what?
I've done some for the next week. Is that right?
That would be appropriate. Sure.
I think the assignments is due on the 9th.
What?
I think it says that the assignment is due on the 9th. Homework 92 is due on the 9th.
It doesn't say this due today.
It's due on the 9th.
Oh, it's a week late. Yes, it should be due today. I will go fix that as well because there's no point in doing it after that, right? I mean, it's to help you on the test. It would help you on the final, that's true, but we do things in units. Maybe a third or less. Claudia.
So the worksheets that we should do, are they the ones from OneNote or the ones posted?
Well, okay, there's 2 sets posted on Moodle. The ones that are in the worksheet section are the updated ones. The ones that are in the chapter 15 section are the ones I used last year. And so I left the old ones there. The updated ones I think are better. There's nothing specifically wrong with the old ones. And the only big difference is that I added a lot more of the conceptual questions to, I think, the chapter 13 or 14, one of those. I refined. What was that? Yeah, because it's the same fundamental problem. So the answers are the same work and the same result. I just changed some wording. So yeah, either one is fine except for you have more conceptual and I've refined the wording. Okay, reviewing what's going to be on the exam. The exam is chapters 13 through 15. So chapter 13, we have the introduction of temperature. And I am reasonably confident that most people coming into a class like this think of temperature as having really no meaning other than hot or cold. But we learn temperature actually does represent something. What is the temperature representing or telling us about? Yeah, how much? Now, we can't say the word heat energy because heat is a transfer process. And in physics, we're really clear on this. In other disciplines, they kind of fuzz the words a little. So for physics, thermal energy is what we say. But it's a measurement tells us about the average, and I've been saying kinetic energy. It's actually the average energy per molecule. And if it's an ideal gas, it's a very simple relation, which we had here, that the total internal energy for a monatomic ideal gas is 3/2 nRT. For a non-monatomic ideal gas, it's the number of degrees of freedom times 1/2 RT, where the number of degrees of freedom is the number of moles times the If it's monatomic, just 3. If it's diatomic, it would be 3, 5, or 7, depending on the temperatures. The ways you can store energy. And so that temperature is telling us about the internal energy that you have, or the average energy per molecule. Temperature scales, obviously you have to be comfortable with Fahrenheit because we live in the United States and that's what we use here. But in physics, you're not going to have any problems that are going to work in Fahrenheit. You might get a problem that gives you a temperature in Fahrenheit, but we do everything in either Celsius or Kelvins. So you have to be able to convert between Fahrenheit and Celsius, and between Celsius and Kelvin. So if you have Fahrenheit and you want to get to Kelvin, you go Fahrenheit to Celsius and then Celsius to Kelvin. And so you have the simple relationships that temperature Celsius, that's a C, is equal to temperature Fahrenheit minus 32, and then multiply by 9/5. Nope, 5/9. And of course you'll have, that's a 32. Can you read that as 32 or does it look like 52? And of course you'll have these equations on the test. And then temperature Kelvin is temperature Celsius plus 273.15. When do you have to use kelvins? When it's just the temperature, when it's not a change in temperature, but just the temperature. If it's a change in temperature, what should you use? Kelvin or Celsius, whatever makes you happy. So yeah, if you use kelvins all the time, you'll be fine, except for the very rare cases when we have like a linearization equation, like when you calculated the, what do you have to do? Oh, you haven't had to do it yet. It'll be the next lab when you calculate the speed of sound in air. Actually, no, you did do it once when you calibrated. The speed of sound in air is a function of temperature. We just linearized that based on the Celsius scale. And so in that case, you have to use Celsius. But in general, either one will work if it's a change in temperature, only kelvins if it's not a change. So using the ideal gas law, that's not a change, you have to use kelvins. Thermal expansion. We had linear and volumetric expansion. Linear expansion was the change in length is equal to the original length times some coefficient of thermal expansion, linear coefficient of thermal expansion, multiplied by change in temperature. So which units do you use there? Kelvins or Celsius. Either one will work. And they'll give you alpha. Some sources will give you alpha in per degree Celsius. Some will give it in per Kelvin. But since a change in Celsius is the same as a change in Kelvin, it still doesn't matter which unit you use. You don't have to match them up. Volumetric, delta V is equal to V0 beta delta T. Just the same, except for you have beta for volume, alpha for linear, and typically beta is just 3 alpha. I don't remember if it was here in class or in my office. I was showing somebody why beta is 3 alpha, but it's pretty simple geometry. Molar and atomic mass. What is the molar mass? It's how many grams per mole of the substance. What is the, I put atomic mass. Okay, I should have said molecular mass instead of atomic. And so it's the mass per molecule instead of the mass per mole of molecules. And so the difference is Avogadro's number. So, and sometimes we use a capital for one, a lowercase for another. I'll try to be clear. I'll either say, one molecule has this mass, or one mole has this mass, or has a mass of this many grams per molecule, or something so you know which one it is. Because you don't want to be guessing. So the difference in the two is Avogadro's number, yes, numerically. So you can always calculate between them, but just know one's mass per mole and one's mass per molecule. What makes an ideal gas ideal? What's ideal about it?
Like completely elastic.
Okay, completely elastic collisions if they hit each other. Otherwise, they don't interact if they don't hit each other. That's one of them. And they have zero volume is the other. Now, these aren't real. They're ideal. That's why we call it the ideal gas law, not the real gas law. And so what approximations can we make to say this behaves approximately as an ideal gas? One has to do with the pressure, one has to do with the density. Or not pressure, one has to do with the temperature, one has to do with the density. If the temperature is far away from the point of condensation, then that means you have a really high kinetic energy for each molecule. And so the amount that it may lose in a collision will be small compared to its total kinetic energy. Hence, it's behaving pretty close to an elastic collision if it doesn't lose very much energy. Remember, elastic collisions mean you lose no energy. If it's going really fast, the percentage of energy lost is really small. And so it's approximately elastic then. Even though you have the same energy loss as you would if it was cold, the amount you lost would have been huge compared to the temperature. So a hot gas is more ideal than a cold gas. So if you're far away from the temperature condensation, by the way, I was thinking about this when I came in this morning. So I got in my car, it's 21 degrees out. And what do I have to do when I get in my car? I have to turn on the air conditioner. It's 21 degrees out and I have to turn on the air conditioner. That doesn't make us happy, does it? No, why do I have to turn on the air conditioner when it's 21 Fahrenheit?
Well.
Go ahead.
Go ahead, Max.
What did you say?
Randy, why? You cannot pretend that was Judith's
Okay, like
voice.
I know that. All I know is the processor has to like start up. You can't like heat up glass too fast or something like that.
Okay, that is a separate thing, and that's relevant to what we're learning. So, what happens when it's cold and I get in my car? Unfortunately, I'm breathing. Okay, that's fortunate actually. When I breathe out, there's a lot of moisture in the air coming out of my body, and so I fog up the windshield. I turn on the AC to keep it from fogging up. Now, why is it fogging up to begin with? I'm breathing out moist air at roughly 98.6 degrees Fahrenheit. The glass is at 21 degrees Fahrenheit. So when air comes to that glass, what happens to the temperature? 98.6 comes to the glass. It drops. But when the temperature of the air drops, the amount of moisture it can hold drops considerably. And so that moist, warm air hits the windshield and becomes super saturated cold air. That is, it has more moisture in it than the air can hold. And so then water droplets form. And they form right there in the window where the air was cooled. And so that's why you get a fog on the window. Or, we say fogged up, right? The window's fogged up because you formed little droplets of water on the windshield. So how do you get rid of those droplets of water? You dry it. There's two fundamental ways. Number one is you could blow dry air on it. And if the air is dry, then moisture will go into the air. Number two is you could blow hot air on it. Because if it's hot air, it can hold more moisture. And so the reason the AC comes on when you hit that defrost in a modern car is because you want to heat up the air as much as you can and dry the air as much as you can. And so first you go through, at least I assume they do it first because it's a logical way. First you go through the air conditioner to dry the air. Because you take the air in the car, you cool it down, and moisture drops out. Which is why you get mold in your AC unit.
So if the AC's on, you get wet, hot air.
If the AC's on, it first dries it because you cool it, and it can't hold as much moisture, and so moisture drops out.
If the AC's off, though.
Huh?
If the AC's off.
No, when the AC is on, this happens.
What I'm saying, what happens when it's off?
Oh, okay, so when the AC is off, then it's going to be hot and moist air. It still will work somewhat because the hot air can hold a lot more moisture. But hot, dry air is going to work better. And so first, you use the AC to dry it, and then you heat it up so you have hot, dry air. It's like a desert, right? So we have a desert hot, dry air.
Well, okay, what if you like, so when you hit like the heater and you're trying to like heat it off, is that cold or high?
It's hot air because first it cools it, then it heats it.
The defrosting does that.
Yeah, I mean that's what the car is doing when you do the defrost in a modern car. It takes a while to get heat, so initially it's just going to be cold dry air, and then as the car engine warms up, then it becomes hot dry air. But the dry air still works. You can, if you can separately turn off the heater, you can just run the. Of course you can. You just call it the AC. You can just run the AC, and you'll defrost that window. You'll just get colder and colder. Okay, so that is. It was bugging me this morning. It's something that's relevant for our test. Then we have the ideal gas law. The ideal gas law is built on 4 laws. So those 4 laws are Charles' law, Boyle's law, Gay-Lussac's law, and Avogadro's law. And I talked about those in class, and even when I talked about them, I said I never really work with these. Because if you combine those 4 laws together, they give you the ideal gas law. So the ideal gas law, I wrote that in red because that's what you need to know. The 4 laws that lead to it are historically important, but each one of them is contained with the ideal gas law that says pressure times volume is equal to some constant K, the Maxwell-Boltzmann constant, or the Boltzmann constant, times the number of molecules multiplied by the temperature. What units does that temperature have to be in? Kelvins. Or using the fact that the number of moles is equal to the number of molecules divided by Avogadro's number, and this gas constant is equal to K times Avogadro's number. Then you can also rewrite this as equals nRT. So those mean exactly the same thing. In chemistry, I think you use exclusively the the green version. In physics, we'll switch back and forth. The red version is molecules, the green version is moles. RMS speed. One of the problems I have lined up to do after I finish reviewing, because I expect to finish early, we'll see, has to do with the RMS speed. What does RMS mean? Root mean squared. How is it calculated? No, square mean root is how it's calculated. First you square your values, then you find the mean or average of those squares, and then you square root it. So RMS is not equal to the average. In fact, how does the RMS always relate to the average? It's always bigger. The average speed is always going to be less than the RMS speed. When we get next semester to voltage, the average voltage is always going to be less than the RMS voltage. In fact, it'll always be 0. But that's why we use RMS voltage. We could use peak. It would make sense, but average wouldn't. Humidity. Now, we've just talked about the fogging of the windshield. It relates to humidity. I use the word supersaturated. What does supersaturated mean? It's over the saturation point. Humidity is a measurement of how much moisture you have in the air, well, relative humidity. Actual humidity is the amount of moisture in the air. But when we say humidity, we never actually mean humidity. We always mean relative humidity, which is why it's in percentage. And it's the moisture in the air divided by the maximum amount, the saturation level. And so if you're at 90% humidity, that means the amount of moisture in the air is 90% of what the air can hold. If you're 100% humidity, it's maximum. What happens if you go above 100%? Then you have water droplets form. And so you have a fog. Or you can have rain. Now, just to be clear, when you have rain hitting the earth, where's the humidity 100%? In the cloud, yeah. It's not necessarily 100%. I used to think, how is it raining and it says it's only 75% humidity? Well, it's here at the surface, but not up there. Evaporation. What is the evaporation process? Yeah, when a molecule comes up to the surface and it has enough energy to break through that surface energy, And so only the higher temperature, the higher kinetic energy molecules have enough energy to break through. The colder ones don't have enough energy and they just come back in. And so what happens to the temperature of a fluid when you have evaporation? It goes down because the hotter ones evaporated, the cooler ones stayed in. That's why things like the swamp cooler work. But it has to be a dry environment, an arid environment, such as in Arizona, for the swamp cooler to work efficiently, because if the humidity outside is close to 100%, you're going to have just as much water coming in as you have going out, and you don't have that cooling effect. Boiling. What determines the boiling temperature for water?
Atmospheric pressure.
Okay, atmospheric pressure, which is related to elevation. It's the atmospheric pressure because boiling occurs when the vapor pressure of the liquid is equal to the atmospheric pressure. Or the partial pressure of water is equal to atmospheric pressure. So the partial pressure of water is equal to atmospheric pressure. And so at that point, the little bubbles start growing, whereas below that, the atmospheric pressure would collapse them. And so boiling temperature, we went through in class and we saw that I believe it was 90 degrees Fahrenheit is the boiling temperature for air in my house in Colorado, because it's at a higher elevation with a smaller, only 70% atmospheric pressure there. I don't know if you guys cared about my little personal note in the message I sent you, but yeah, we had like a foot of snow and lots of fun with the grandkids. Chapter 14, heat and heat transfer methods. So make sure it's clear to you what heat is. The heat is a transfer of energy, not involving work. So work was force times the distance parallel. Heat is a transfer without that. Heat transfer occurs because you have, well, we usually talk about in conduction, one molecule hits another molecule and it transfers energy. It's like, billiard balls. One ball slows down, the other one speeds up. You transferred energy. That's how conduction works. But we have three mechanisms for heating. We have conduction, direct contact. We have convection. What is convection? You have an intermediary that's transferring. Yes. Andy's good with the hand signs for these things. Remember conduction? Yeah. So convection and intermediary. Convection is actually really important. Let's say you live by the ocean. You have lots of ocean breezes, right? What causes those? The ocean. Convection, because I'm talking about it, for crying out loud. Let's just imagine that you live off the coast of California.
Florida.
Okay, you could live off the coast of Florida too. You just wouldn't be as lucky.
You'd be luckier.
We're from different coasts. Nothing wrong with her humid coast and my dry coast. So we have water. It's like lotion. The air is like lotion in Florida. Okay, water. What is unique about water? There's a couple answers to that. What's unique about water? It's what? Okay, hydrogen bonding causes it to have a very large specific heat. I don't know if that's actually related to hydrogen bonding. I haven't thought about that. The what? I couldn't hear what you said. It expands. Yes. Expansion when it freezes is the other one that I think of as a very unique property for water, and that's definitely because of hydrogen bonding. So water, in this case, specific heat of water is large. What that means is, remember, for heating and cooling, Q is equal to MC delta T. So in the daytime, you have a lot of sun shining on the water. And so it absorbs a lot of heat. Now, the ocean has a big mass. Specific heat of water is big. So what happens to the temperature of the ocean water when you have all of this energy absorbed? Not much. So the water temperature doesn't change very dramatically. And so, depending on the time of year in California, this water might be at 50 degrees Fahrenheit. Now, if you're in Southern California, You have out here land mass, which has a much lower specific heat. So you have the same sunlight hitting the ground, but what happens to the temperature of the ground with its lower specific heat? It heats up a lot. And especially if it's asphalt. Why would asphalt heat up more than, let's say, sand? It's black, and so it's going to absorb a lot more radiation. Yes?
How is some sand black?
Well, sand is largely silica-based, right? That is quartz. But your rocks are not all quartz. You have impurities. You have things like magnesium, iron. And so you have other minerals in your rock besides quartz. So if you have, plagioclase, it's going to be pinkish sand. And if you have, feldspar, you're going to have some black regions. And so that's how you get the different temperatures, different minerals for your rock. But they're still going to be fundamentally the specific heat of quartz, because that's what the dominant thing is.
The specific heat can be changed by the color?
The specific heat is going to be affected by the mineral composition, but for the most part, you're primarily quartz in your rocks. That's the primary component of most rocks. And so the specific heats can be pretty similar. She was asking about colors. And the absorption of radiation is very dependent on the color. And so something black like asphalt is going to absorb a lot. Now, asphalt is, of course, that's tar. It does have a different specific heat from normal rock. But
when we're talking about color, we're going to relate it to radiation.
yes. So the ground has a lower specific heat. It absorbs roughly the same amount of radiation. What happens to its temperature? The ground?
Oh, the ground.
The ground gets much hotter. And so your ground temperature might be, let's say, 90 degrees Fahrenheit. So air above the water is going to be in equilibrium with water, cold. Air above the ground is in equilibrium with the ground, hot. So what's going to happen to the air? The hot air, what does hot air do? It expands first. It expands because hot. That is our delta V is equal to V0 beta delta T. But because it expanded, you have the same mass in a larger volume. That means its density dropped. And what happens to lower density materials? They float. And so this hot air floats upward. And that means that this cold air, which is, less or more dense, is going to move in. And so during the daytime, you'll typically have a breeze blowing in from the sea because the cooler air is coming and filling in the places where the hotter air has risen up. Now, what happens to that hot air as it rises? Why?
Because it's further from the thing making it hot.
Further from the thing that's making it hot. That is a true statement, but it's not the one we rely on. The one we rely on is the thermodynamics that says that as it rises, the pressure drops. And if the pressure drops, PV equals nRT, it's going to expand and cool. And so it expands and cools. Yeah. It doesn't really have much volume to expand. It expands upward. And so it starts cooling as it goes up. Now, you have some funny things in weather, so it's not a continuous process forever that reaches a place where it reverses. But it expands and cools, and so now you have colder air up here. The colder air is then going to, when it reaches equilibrium, start condensing again. And so then you have up atop cold air. Trade winds make the air so it moves over like this. So here you have cold air because it's risen. It moves over here, and then it comes back down. And as it comes down, it compresses and heats. And so you have a cycle that's a convection cycle. And this is actually the reason we have deserts. Deserts occur roughly 30 degrees north and south of the equator. Because the equator, what do you know about the equator? It's hotter. And you have a lot of moisture there. It's pretty much ocean on most of the equator. So you have hot, moist air that rises at the equator. And then because of the Coriolis effect, remember we've talked about the Coriolis effect, when it gets up there, it'll move north or south and deviate, creating trade winds, and then it moves and drops down. And it drops down at about 30 degrees north or south latitude. And so that's where the majority of our deserts are, because as it went up and cooled, what happened to the moisture? You take hot, moist air, and as it rises, what happens? It's going to get cold, which means that it's going to have the humidity go up until you reach saturation, and it drops the moisture out. So in a tropical place, you get rain every day because you have that moist air going up, cooling, and then dropping the water back down. And so then you have dry, cold air. It drops down, becomes dry, hot air. When it hits the ground, that dry, hot air absorbs any moisture that could have been there and makes your desert. So that's an example of convection in action. And if you, well, I'm not going to talk about the Santa Ana winds are a little more complicated, so I won't go into that. So that's a lot on convection. Radiation. How is radiation a mechanism for heat? You have electromagnetic waves, which we'll learn next semester is the same thing as light waves. Light waves are an example of radiation. This here is a dewar. A dewar is what you have in your copyrighted thermos. When you look at the dewar, you have a number of things to know. First of all, the color. What color is this? Okay, it's silver. Why silvered? It's reflective. It has the lowest possible emissivity. Emissivity tells you about the efficiency of absorption and emission of radiation. So if it's silver, it's very poor at absorbing radiation. It's also very poor at emitting radiation. What color would make this really good at absorbing radiation? Black. What color would make it really good at emitting radiation?
White. Or silver.
Because that's emitting radiation. Wouldn't that be black?
Yes. If it's good at absorbing, it's good at emitting. So black is the answer to both questions. Silver is bad at absorbing and bad at emitting. Part of the reason why a thermos keeps hot things hot and cold things cold. Second thing is, if you look, well, if you feel it, like you tap it, you can tell this is thin glass. But it's got this thick wall because it's double walled. What do you suppose is in between the two walls? Air is a good insulator, but there's something better.
Nothing.
Vacuum, nothing. So this is evacuated. Why evacuate? If it was air, you would have poor conduction, right? Because air is a very poor conductor. What's an even worse conductor than air? Vacuum, because there's nothing. Convection. Convection, you have to have an intermediary. If it's in vacuum, there's no convection. So the only way that heat can flow from the outside to the inside is by traveling this long distance here. It's thin, so the area is small and the length is large. So you have very small amounts of conduction that occur. You have no convection from the inside to the outside. You have virtually no radiation absorbed by the outside or radiation from the outside to the inside. So the inside, if you put a cap on that's equally good at insulating, it's very well insulated because it's covering all three of the mechanisms. And then there's the joke about the person who puts their ice cream and their hot pizza in the thermos together because it keeps hot things cold, or hot things hot and cold things cold. But what happens when you put the hot and the cold together?
Equilibrium.
The second law of thermodynamics says that heat's going to transfer. If it's isolated like this, it's just going to transfer from the hot one to the cold one. And so the temperature, if you put the two in, isn't going to stay constant for each one, which we all understand. That's usually told in the guise of a joke that's, inappropriate for us here. Okay, phase diagrams. We had two types of diagrams we talked about. We had pressure temperature and pressure volume. So with what's the one we always look at? Those are the two examples we use, but the the axes, pressure and volume. Right, there's our phase diagram that we usually look at, PV. In that PV diagram, if you're looking at water, it goes like this. This line up here, actually, it dimples the other way. Everything you see in a textbook stops way down here. So it doesn't show this feature. And so the water, it has a slope going to the left between what phase is over here at low volume, solid. Which one is out here at high volume? And under this region, what is in there? Liquid. Okay, now we have some important points. Important points, and at least one of these is a question on the test. Okay, which one's the triple point? Okay, the one where all three lines meet is the triple point. What's important about it being you get many more than one. What's important about the triple point? Okay, it is the only pressure and volume and, of course, temperature where all three phases coexist. Any other combination of pressure, volume, and temperature, and they don't exist. On this diagram, it doesn't show temperature, of course, but it is a specific temperature. For water, what is the triple point temperature? Temperature triple point for water is equal to 273.16, no degree sign, kelvins, or 0.01 degrees Celsius. You actually should know it. I'm not going to test you on it, but you should know it because it's an important number. That is, it was part of the calibration for the Celsius or Kelvin temperature scales was the triple point temperature. What do you call this other point out here? It's the what point? The critical point. What's the importance of the critical point?
Past it, there's like a phase that's not quite liquid or gas.
Okay, that is the highest pressure and the highest volume where you can differentiate between liquid and gas. So if you have a higher temperature than the critical point temperature or a higher, I said temperature, I didn't mean that, a higher pressure than the critical point pressure, or if your density, I mean, when you look at volume, you're like, wait a minute, how does that relate to reality? Well, it actually relates to density. But if you're beyond that in volume, that is if your density has become smaller, you can't differentiate between a liquid and a gas.
But you physically can't, or like you make it out of CAD?
No, there is no differentiation. It doesn't exist. So that's what the importance is of that critical point. Let me just ask, what's going on right here? It's changing phase is the answer. But it's still solid on the left side. It's just changing from one solid structure to another solid structure. So we have different names for, water 9, water 11, for the different solid structures that it has. And that wouldn't be on the test either. But it's the kind of stuff that I think is useful to know. Calorimetry. If you're doing a calorimetry problem, this is a multicolored pen. If you're doing a calorimetry problem, what's the key? If you have something that's insulated, so Q net is 0. And then heat flows from hot to cold. So if I take like hot iron and put it in water, I say the heat for the iron is going to be Q equals MC delta T, which is temperature final for the iron minus temperature initial for the iron. And for the water, it's going to be Q equals MC delta T, where now delta T is temperature final for the water minus temperature initial for the water. And I add those together, assuming that I have like styrofoam, which has essentially no specific heat. And my total heat is 0, and I can solve for temperature final if I know the temperature initials of the two. Or if I know the temperature initial one and the temperature final, I can solve for the temperature initial of the other. There's lots of permutations on the problem, but they're all sum of the heats is 0, and you have to add up the heats. Now remember, when a material is changing phase, what's going on with heat? Heat goes in, what happens? Instead of that heat making molecules move faster, which we would call a rise in temperature, what's the heat doing when I'm changing phase? Say I have a solid. Solid, the molecules are in fixed positions, they do little vibrations. And if I put in heat, it breaks the molecule free of its location, so the energy went to breaking it free instead of making it have a higher energy. So the temperature stayed the same, but the phase changed. And so we had the equation that I already wrote over here. This is what's happening while it's in one phase. But if it's changing phase, Q is mL, where L is the latent heat. It could be latent heat of fusion or latent heat of vaporization. It's the heat per mass required for it to change phase. Final chapter. Wow, I really intended to do the problem that you asked me about. It doesn't look like we're going to get there. Chapter 15 is thermodynamics. Thermodynamics is a lot of fun, but there's also some tedium, as you would see looking at problem 5. So first law of thermodynamics, let's review all the laws of thermodynamics. What's the 0th law? Okay, everything perfect except for we should say temperature. Temperature A equals temperature B, and temperature B equals temperature C, and temperature A equals temperature C. It's just a whole lot more syllabus to throw into it. So, and in reality, we say if object A is in thermal equilibrium with object B, but that means that temperature A is equal to temperature B. Second, the first law. What's the first law of thermodynamics? Conservation of energy. Somebody said on Perusal, it's like conservation of energy. No, it is. That's what the first law is. Energy cannot be created or destroyed. And then immediately somebody is bound to say, well, what do you mean? I mean, we have all of these power plants that produce energy. Au contraire, what do they do? What does a power plant do? It converts energy from one form into another. It could be converting from nuclear energy into, well, it converts it actually into thermal energy and then uses a heat engine to go from thermal energy into a usable type of energy. Or we could have a fossil fuel that we burn, converting the chemical energy into thermal energy, which then we use for a heat engine to create mechanical energy. Or we could have something that doesn't involve thermal energy in a direct way, a photocell. A photocell converts radiation energy into electrical energy. So they're not producing energy, they're converting it. Okay, so that was the first law of thermodynamics. Second law of thermodynamics. I have 2 of them written up there, actually.
Heat goes from hot to cold.
Heat goes from hot to cold. Heat naturally flows from hot to cold, never from cold to hot. What's another statement of it? There is no process that can be made to decrease the entropy of the universe. Now, a concept I didn't talk about that is actually an important concept, but not very practical, is heat death. When you get down to it, basically everything we have runs on heat engines, converting thermal energy into mechanical energy. We use that mechanical energy, we have things like friction that return into thermal energy, but we say it degrades it. It raises the entropy, which ultimately means that we're decreasing the temperature difference between our hot and our cold. To have a heat engine, you have to have a difference. If everything reaches equilibrium, if everything in the universe is the same temperature, then we have what's called heat death. There's plenty of energy, but we can't use it because we need to have temperature difference to have a heat engine that works. Remember, the Carnot engine was the ideal engine. Ideal engine, you have an isothermal process, then an adiabatic, then isothermal, then an adiabatic. And Carnot was able to show mathematically that that's going to give the highest possible efficiency. And that efficiency for the Carnot engine was equal to 1 minus temperature cold over temperature hot. What happens if temperature hot is equal to temperature cold? What's your Carnot efficiency? The The best possible efficiency you can get if temperature hot is equal to temperature cold. What does that come out to be? 1 minus 1, which is 0. So you can't get any mechanical energy out if you have same temperatures. So that's what the concept of heat death actually is. Efficiency, as your homework drives into you, our homework site uses eta for efficiency. That's a Greek E. Is equal to what you get out. What are you trying to get out of a heat engine? Work. So it's your output work divided by what you put in. What do you put into the heat engine? You put in heat at high temperature. It's going to exhaust heat at low temperature. You put your hand on the tailpipe of a car, and you'll feel that heat at a low temperature. It doesn't feel very low, does it? It'll burn you badly. But it's cool compared to the temperature of the gas when it was burning in the piston. And so it's the temperature hot is the temperature of the piston, the temperature cold is the temperature of the exhaust pipe. Entropy. What is entropy? We have the answers: disorder and chaos. Entropy is a measurement of how many ways you can arrange a system to get the same pressure, volume, temperature. And it turns out if you have a system that contains 10 to the 24th molecules, if you look at the number of ways you can arrange them, it goes like this. It's a very strongly peaked function. And so that means the probability of being at that peak is very high. The probability of being anywhere except that peak is very low. And so entropy is a measurement about how many ways you can get this arrangement. And because it's so strongly peaked, we talk about it like it's a law, but it's really a statistical statement. The second law is saying that every process can only produce higher entropy. You can never lower it. What that really says in layman's terms is every process is going to do the most likely thing. Now we know in reality, every process doesn't do the most likely thing. I can have a die that has 6 sides that have 1 pip. Oh, no, that would be, if it's a 6-sided die, that would be all of it. If it's a 6-sided die, I can have 5 sides with 1 pip and 1 side with 6 pips. And when I roll that die, you've got a 1 in 6 chance of getting 6 and a 5 in 6 chance of getting a 1. So the probability is much higher for getting a 1. But that doesn't mean you're never going to get a 6. Same thing with the second law of thermodynamics. It is physically possible for something to violate the second law of thermodynamics. But when you have a system with 10 to the 24 or more molecules, the probability is so low that we call it a law. It says it's not going to happen. So that's statistical interpretation of entropy. 2 minutes. I did this instead of PowerPoint using this so I could work out the problem. 2 minutes. Let me point out just one key, and then we'll have to be done. This one key is something I forgot to say in class. Do you remember when I talked about 2 processes going like this? Which one's which? Okay, it should be isothermal is on top and adiabatic on the bottom. The Y is for isothermal process, PV is equal to constant. So that means pressure is equal to initial pressure, initial volume over the volume. And so you have that inverse relationship. For an adiabat, it turns out that pressure times volume raised to the gamma is equal to constant, where gamma is defined as Cp over Cv, which for a monatomic ideal gas is 5/2 over 3/2 or 5/3. So this ... is for monatomic ideal gas. Now, a Carnot cycle has only isothermal and adiabatic processes. So if you look at this picture, you can use the 1, 2, 3, 4 to tell that it's going this direction. And so actually you had this diagram before in one of your multiple choice questions, which one follows. And Actually, it wasn't like that because it went like this. It was squared off in the bottom. But it had these two. Between going 3 to 4 and 4 to 1, which one's adiabatic and which one's isothermal? Okay, 3 to 4 is it flatter or steeper? Flatter. This one here is going to be the isothermal. Another way to do it, it's all, okay, Carnot cycle is alternating isothermal adiabatic. We can look at these two because these two, 2 to 3 and 3 to 4, are exactly what I had in my picture. So the upper one had to be the isothermal. And then, so isothermals are going to be those two, and adiabatic are going to be these two. Now, in solving this problem, I've gone 1 minute over, so obviously I'm going to stop now. In solving this problem, you have those two relationships, this relationship and this relationship, and the ideal gas law. And between those, you can solve the whole problem. You have to say, okay, what happens to PV when I go from 1 to 2? Well, because it's isothermal, it stays the same. But if V went up by a factor of 4, then what pressure have to do? Just using that equation, it had to drop by a factor of 4. And then going from B to C, it tells you the temperature doubled. If it's an ideal gas and the temperature doubles. I didn't write PV equals nRT on this. If temperature doubles, then PV doubles. And so you know that PV doubled, and you also know that PV to the gamma is constant. And so you have two equations that you can solve then for the P and V at step 3, and likewise for getting to step 4. All right, we're totally out of time and 2 minutes over. Sorry about that. I'll see you for the exam tomorrow, except for Randy and David. We'll see you guys tomorrow at 11:30.